Okay, hi everyone. So this is chapter 6 on inner products and norms. Okay, so let's start with number 1. Why don't you pause the video and read this? Maybe try it yourself. Okay, so V is a real or complex space. An inner product assigns a number, which could be like a complex number. Okay, so it's like a dot product, but now if we're over the complex numbers, the dot product of two vectors could be a complex number. So keep that in mind. We'll need to think about its conjugate and its real part and its imaginary part. So let's try to remember these definitions. So an inner product satisfies positivity, meaning if you do v dot v, you should always get greater or equal to 0. Really, this should be non-negativity, but they call it positivity in your book. Definiteness means that if v dot v happens to be equal to 0, that means that v was the 0 vector. Okay, you don't get to have vectors that are orthogonal to themselves unless you're the 0 vector. This changes in special relativity where you have pseudo inner products. Time and space get a different sign. It also changes if you just have a bilinear form on the complex numbers, and you can have isotropic subspaces, and that can be important too. Additivity in the first slot means that if u plus v and is inner product with w, that's just the inner product of each term separately. So it's linear in the first slot. It's also linear in the second slot, except for the fact that you have to pull out a conjugate. So let's see what that means. If we have a complex number in the first slot, we're going to pull it out just like normal. But if we have a complex, so that's homogeneity in the first slot. If you had the same thing but the complex number was over here, then when you pull it out, you have to do a bar. Physics does this the other way, so just pay attention. It doesn't really matter. Physics thinks that the second slot should be kets, which are vectors, and the first slot should be bras, which are covectors or in the dual space. And this can be really useful for Dirac formalism, where you have to take the Schwartz space, which is inside of L2, which is inside of the dual of the Schwartz space, but that's neither here nor there. Conjugate symmetry means that if u dot v is some complex number, then v dot u is just the conjugate of that number, right? So if this happened to be the complex number u dot v, then, I know it looks like a vector, but it's a complex number here. So u dot v is a complex number. Maybe u and v are vectors in c to the 10, right? And we dot them against each other, we inner product them, and we get a complex number. Then the conjugate of that number is down here in the complex plane. And what I'm saying is that's just the inner product of v with u. So switch the order. Okay. So in particular, if we add uv plus vu, that's equal to twice the real part of uv, because of how complex numbers add. If we do this plus its conjugate, that brings us over here, which is twice the real part. Okay, so that'll be important later. And I forget what we're going to use that. Maybe the triangle inequality. Okay. The Euclidean inner product on Fn. So this is the reason for all this stuff with the complex conjugate is we want to get real numbers out. Okay, we want to have to be able to think of this inner product as measuring the size, even when we have vectors in C10. We want to know what the size of a vector in C10 is. And so we want u dot u to be actually a real number, and in fact, a non-negative real number, so that we can interpret it as a size. In order to get that to happen, if u is in C10, to do u dot u, we can't just do like normal where we do u1 squared plus u2 squared plus u3 squared like Pythagoras up to u10 squared. We can't do that because this will not be a real number in general. So what we have to do is we have to do u1 bar plus u2 bar plus dot dot dot. Okay. So for example, if u is in C2, maybe u is the vector 1 plus I, 1 minus I. Okay, that's a vector in C2. Each of its components are a complex number, so I might call this one u1 and this one u2. And if I want to create the sort of the length squared, the size of u, then we're going to call this the length squared or the norm squared or the magnitude squared of u. Then what I'm going to do is I'm going to do u1 bar plus u2 bar. And that will give me a real number, because in this case u1 is 1 plus I in my example. u1 bar is 1 plus I bar. But that's just going to be the squared length of this complex number, which in this case will be 1 squared plus I. Okay, I mean, maybe I'll just write this out. When we conjugate, we get that. And then we're going to just FOIL out. We get a plus I, we get a minus I, we get a minus I squared. But that's just 1 plus 1, which is 2. Okay, so that's the length squared of the vector 1 plus I in the complex numbers. It's just, it has a length square root of 2, and length squared is 2. So that's going to give us a 2 plus a 2, which is 4. And 4 is a real number. So it allows us to sort of think about the size of a vector in C2 or C10 or wherever, or any complex vector space with a inner product. So the formula for the Euclidean product on Fn is, we're going to take uv, and we're going to take, u is in Fn, so u is a vector with components, etc., all the way up to un. And then v is a vector also in Fn with components v1, v2, v3. Careful, these are not basis vectors. These are the components of our vector, even though sometimes we call a basis v1, v2, v3. Now, these are actually just numbers in the field. Okay. And what we're going to do is we're going to do u1, v1 bar plus u2, v2 bar plus plus un, vn bar. In contrast, when we were in multivariable calculus and we had vectors in R3, like u and v in R3, we would do the dot product u dot v, and that was u1 v1 plus u2 v2 plus u3 v3. So you see that this formula reduces to the old formula when our vector components are all real numbers, because then the conjugate of a real number is just the real number itself. So this is just the usual dot product when we have the real number field, r to the n. But if we go to the complex number field, c to the n, we actually start using these conjugates, and that allows us to get that u dot u is a real non-negative number. All right, because that's just what we want. We want this dot product to sort of measure the size. Okay. Take a look at number 3. Maybe pause the video to try to remember what has to be true. Okay, so what has to be true for each of these coefficients? We're imagining that these are coefficients in the field. Well, they should be real, okay? Because otherwise we're not going to get a real number out. So these things have to be real and non-negative. All of these, in order to get to define an inner product, we have to have positivity when we take w and z equal to each other. We want to get that it's always a real number greater or equal to 0. And so that's why we need these coefficients to be non-negative and real. Okay. Can you remember the 3 examples of inner products in the textbook? Well, I don't know, but I'll just give you a couple of them. You could just, if you take some polynomials, you could integrate them over any interval, right? You could take p of x and q of x and just integrate them over an interval, and that would work. That's going to give you an inner product. For example, how is it going to be non-negative if we do p dot p? So this is p dot q. P dot q might be this. But if we do p dot p, we're going to get p of x squared. And if you integrate something that's that's non-negative, you're going to get a non-negative number. So there's all those properties we have to check, but I'm just talking about the positivity right now. Some other ones that are good is that sort of just like up here when we had these coefficients had to be non-negative, we can just throw in, when we're integrating p of x and q of x together, if we throw in something that's non-negative, like e to the anything is non-zero, and you might be wondering why I do the e to the minus x. Let's say I did e to the x and I tried to integrate from 0 to infinity, this would explode and I wouldn't get a finite number. So that's why I put a minus x, so this e to the x thing sort of dies down when we go to infinity, and we can get a finite number out of this. Okay. And these kind of integrals will be useful in things like the Laplace transform if you put like a, I don't know, an extra variable in here. I don't know what. We're not going to talk about Laplace transform, but there's some other. You can think of these as weighted inner products, and e to the x is a weighting function that is not negative, so it doesn't destroy positivity. Okay. I don't know if there's. Did I give 3 examples? Oh, there was another one in the text that was kind of interesting. You'd take the inner product of p and q when they're polynomials, and you might define it to be equal to the evaluation of p and q at a point, maybe the point 0. I think we could take any point here, not just the point 0, and multiply it together, and then we can add sort of anything like we did before, or like maybe an integral. And so there's all sorts of these different inner products that you can define that are useful for different purposes in, say, partial differential equations. Okay. So let's look at number 5. Maybe pause the video and read it. Okay, so maybe we won't prove all of these because they're proved in your book, but let's just talk about the meaning. So if you fix a vector, then you can take other vectors and dot them against your fixed vector, and that actually gives you a map sending any other vector to the field. Okay, and this map is linear because if you fix v, remember we had linearity in the first slot. So this is a linear map because if you do this map to u plus w, you're going to get u plus w v, and then that, by the properties of inner product, is like that, which is just the map applied to u and added to the map applied to v. So this is a linear map, and it's a very important one. And in particular, linear maps from, remember, a vector space to another vector space are important to us. They were the subject of chapter 3. Here's a special case where the second vector space is actually a one-dimensional space called a field. And these are particularly important, just like we've been studying in chapter 5, linear maps from V to V called operators, and those were important. These are also important too. They're called the dual vectors or covectors. In the Bra-Ket notation of quantum mechanics, they're the Bra vectors, are essentially dual vectors. So just be aware of them. We're going to use them a little bit later. Okay. Apparently, if you take any vector and dot it with the 0 vector, you get the 0 number. Okay, so remember, this is the 0 vector. You have to feed vectors into the inner product. And so this must be the 0 number because the inner product takes 2 vectors and spits out a number. And this is pretty easy to prove just because if 0v, we'd like to show, is that equal to 0? Well, we know that 0 is 0 plus 0, and by linearity, we get 0v. Okay, so this is equal 0v plus 0v. And now read, this is equal to this. Now subtract one of these terms off, and we get 0 is equal to 0v. So do that one yourself. It's a similar trick to what we did earlier in chapter 1. Okay, so we do have linearity in the second slot. It's just only the additive linearity, because if we started to scale something here, we would need to pull out a C conjugate. Okay, so it's not quite linear. Maybe you call it anti-linear. I don't know, but that, as long as you're not scaling things, vector addition is preserved in the second slot and the first slot. Okay, and then this one, if you scale the vector in the second slot, okay, you're kind of missing it there, but you see there's a bar. It pulls out with a bar. Okay, and I mean, let's just prove that. Remember, we had said that one of the properties was that u.v and v.u are not equal. So this would be false, but if I go like this, if I put a bar, it's equal. So that means if I take u lambda v, it's equal to lambda v u, but with a bar. But that's equal to, now I can pull the lambda out of the first slot without a bar, right? vu. And so then the bar of 2, this is a complex number times a complex number, and we know that you can just distribute the bar to each of the complex numbers. But then we know that that's lambda bar and then uv, where I've taken away the bar because I've switched the order back. And so that finishes the proof of this. Maybe pause it, do it yourself. So take a look at this one, pause the video. Okay, so let's give 2 examples of the norm in specific spaces. So let's take vectors in R2 and the usual Euclidean norm. Then if you have a vector, I don't know, x in R2, then what is it? It'll be the norm of x will be the square root of x dot x, which is the square root of x1 squared plus x2 squared. In other words, Pythagoras. This is just Pythagoras in a Euclidean space with the usual dot product where x dot x is defined to be x1 bar plus x2 bar. Okay, this is the Euclidean inner product. And because we're in the real numbers, conjugating doesn't do anything, so we just get x1 squared, and this becomes x2 squared. Okay. Another example would be those polynomials. If we do p dot p and then square root it, we get the norm of p. Okay, I mean, I honestly like to think of p squared is p dot p. Well, what the inner product allows us to do is measure the squared length naturally. The square root is kind of annoying, so I like the squared length to think in terms of that. These are saying the same thing. But now what? Oh, I have to give the explicit formula. So maybe we're going to use one of those inner products where we integrate them against each other. Okay, p of x and p of x is just going to be p of x squared dx, and I have to put a square root. So there's an explicit formula for the norm of a polynomial in some inner product space. And I remember this definition here was just there's many other definitions for inner products on function spaces. Okay. Let's prove this. Why is this true? Well, the key, like I just said before, is I prefer, inner products are best with the squared norm. Okay, so I'm going to just immediately square this and then start manipulating and see if I get this squared. If I do, then I just take the square root and I get the proof. So let's actually start by squaring this. Well, that is by definition lambda v dot lambda v. But that is, I can pull out this lambda, this first lambda, without a bar. And then I can pull out the second lambda with a bar. And now what do I have? I have the complex number magnitude squared. A complex number times its conjugate is just its magnitude squared. And I've got v squared. But that's exactly the square of this right-hand side. So taking square roots gives me my answer, and I'm done. That's the proof. 2 vectors are orthogonal if uv equals 0. Then we call u and v orthogonal, or perpendicular, or 90 degrees. Prove that 0 is orthogonal to every vector. So 0 dot v should be 0. Oh, we already did this proof, right? It's 0 plus 0 v. So 0v is equal to 0 plus 0v is equal to, by linearity, this, and now I subtract this from both sides, and I get a 0 equals u dot v, which is what I was trying to prove. Okay. 0 is the only vector orthogonal to itself. That was just by definition of our inner product. Remember, definiteness said that v dot v equals 0 implies that v is the 0 vector. That was just built into the, you can't prove this. You can't prove it, it's just a definition, at least in our book. Okay. Remember, there's always different ways to set up the axioms of definitions. Remember, we had like 3 equivalent characterizations of a direct sum of subspaces. So you could take any of those 3 and just declare that's my definition, and then you'd have to prove the other 2. Similar thing here, there's different ways to do it. Okay, this is a really important one. I like all these next ones are really important, and I think I'm going to do these a little differently than our book, okay? And I'm going to follow Lang's calculus of several variables because I really like how Lang does it. And you'll have seen this all in Math 155. Okay, so what's the Pythagorean theorem? Okay, the Pythagorean theorem is about right triangles, okay? So if I have a vector u and a vector v that are orthogonal to each other, that's when the Pythagorean theorem applies. And what does it say? It says that the sum of squares is equal to the hypotenuse squared. In other words, u squared plus v squared is equal to the hypotenuse squared, equal to the hypotenuse squared. So if uv equals 0, this is true. That's what Pythagoras says. If you have a 90 degrees triangle, then the squared plus squared is that a squared plus b squared equals c squared. All right, so let's just compute u plus v squared is by definition u plus v, which is uu plus vv plus uv plus vu, and this is u squared plus v squared plus 0 because they are 90 degrees. We really need that 90 degrees thing. Otherwise, that would not be 0. And so that's the end of the proof. Okay, that's Pythagoras. Now, we're going to prove one of the most important inequalities, Cauchy-Schwarz, but it's very easily proved if you understand projection. To project a vector u onto a vector v, and we'll call it a new vector p, the projection. And so here's the picture. You need to practice doing this. Let's project onto this vector v, and we'll project the vector u onto v. What that means is we take the shadow, the 90-degree shadow, and it gives us a vector p. Now p is by definition some scalar multiple of v, because we project u onto v. That means we're going to have some scalar multiple of v. Okay? If we were projecting v onto u, we would get something over here, 90 degrees like that. But that's not what we're doing, okay? We could do that, but that's not what we're doing here. We have to project one onto the other, and the order matters. Okay, so let's project u onto v. Well, by definition, we've got a 90-degree angle there. But that means that this vector, u minus p, is orthogonal to v. Of course, I could have written p here again, but that wouldn't be smart. It'd just be making my algebra harder. So this vector here is going to be orthogonal to this vector here. They're going to be at 90 degrees. And that's what's going to allow us to solve for this scalar multiple c. C will end up being uv over vv. That will be the scalar multiples, right? This is a number, and that's how much we should scale v by to get the projection p. But let's see that come out. So we use linearity, uv minus pv equals 0. But what's p? P is the unknown scalar times v. So if I replace p with cv, I can pull the c out, and I get uv minus c times vv equals 0, and I get that uv is equal to cvv by adding this to both sides, and then I divide by that, and I get that c is this. Okay. So to project, the projection of u onto v is just uv over vv in the direction of v. So this is the vector part, this is the scalar part. Okay. Now, what we're going to do is just prove Cauchy-Schwarz by just throwing away one side of the Pythagoras triangle. We have a Pythagoras triangle here. When we project a vector onto another, we have a Pythagoras triangle, and what we know from Pythagoras is that the length of the hypotenuse squared, which now the hypotenuse is u, it's not u plus v anymore. It's the hypotenuse is the vector u. It's equal to this squared plus this squared. So it's equal to p squared plus u minus p squared. And that's Pythagoras. But what we're going to do is throw this away. If we throw away a number that's positive, we have made this side smaller. And that's where the inequality is going to come in Cauchy-Schwarz. So then we just unpack what this is. Remember, P was CV, right? CV squared is less than or equal to U dot U. U squared is U dot U. You really got to put that in your mind. U squared is U dot U. And then this is now a C squared and a V squared less than or equal to U. And what's C again? Remember C was U dot V over V dot V. Okay, so C squared is going to be UV squared over VV squared. And V squared is VV. So one of these will cancel one of those. And we multiply this to the other side. And we'll get UU VV greater or equal to UV squared. And now I'm going to just take the square roots of both sides. And what I get is that the absolute value of UV, or the norm of UV, is going to be less than or equal to that. Okay, usually I think it's stated the other way around, that this is less than or equal to U. Obviously, these are equivalent. So, in my mind, the easiest way to prove Cauchy-Schwarz is think about projection and just throw away one of the sides of a Pythagoras triangle. Okay, and out pops out Cauchy-Schwarz. And now let's look at the triangle inequality. This is a little trickier because we've got complex numbers. What's the triangle inequality? It says that if you go someplace, the shortest path is just to go straight there. So if this is u and this is v and this is u plus v, the triangle inequality says that u plus v is less than or equal to u plus v. Okay, so, and that makes sense. Like, if you're going to go somewhere, just go straight there. That's the shortest way to do it. So, well, as usual, what I told you before is that inner products are best suited for squared lengths. So let's just square both sides of this. Okay, then I get u plus v norm squared less than or equal to. Now squaring this is like a FOIL kind of situation. I have to square, and then I get plus 2 u v. Okay, that's how you square a plus b is a squared plus b squared plus 2ab. Okay, and now what's this? This is by definition u plus v dot product, which is u plus v plus vu plus uv. There's 4 terms here, expanding this out. And this is, so what we're going to do here is if we're going to cancel this with this, cancel this with this, and now we're asking ourselves, because we're wondering, is this true? We're asking ourselves, is it true that uv plus vu is less than or equal to twice the norms of that? All right, we canceled these other ones, so all we're left is that. And is this true? Right? Well, remember now, this is a complex number and it's conjugate. So that is equal to twice the real part of uv. And we're wondering, is this true? Okay, but the real part of the complex number uv is certainly less than, so twice the real part of a complex number u dot v is certainly less than or equal to twice the length of that complex number uv. Right? If you have any complex number, its real part is less than or equal to the length. Okay? That is a property of complex number geometry. Really just Pythagoras in the plane. And so what's this? This is Cauchy-Schwarz. We can say now this is less than or equal to by Cauchy-Schwarz uv. And we're done. That's what we wanted. Okay. So we needed to use Cauchy-Schwarz to prove the triangle inequality. And we needed to remember that a complex number and its conjugate added together gives twice the real part. You gotta know that picture. Here I am in the complex plane. If I have z and I have z bar, you add them together, you're over here, that's twice the real part. It's a real number. Z plus z bar is a real number. It's twice the real part of z. Z minus z bar is a complex number, pure complex. It's twice the imaginary part of v. So z minus z bar is twice the imaginary part of z. Okay. It's going to come up again. It's going to come up again. In fact, well, anyway, let's just wait until we get to adjoint, self-adjoint, skew adjoint. Parallelogram law is kind of fun. So if you have any two vectors, u and v, you can form a parallelogram by just then copying u up here and then copying v up here. And what does the parallelogram law say? It says the sum of squares of the diagonals is equal to the sum of squares of the perimeter. Okay, so let's just start with the sum of squares of the diagonals. Do you agree that this long diagonal is u plus v? So its square is u plus v squared. Now what's the shorter diagonal? It's u minus v. U minus v, final minus initial. So then we're going to take u minus v and square it. And here's the sum of squares of the diagonals. And we're going to ask, is this equal to the sum of squares of the perimeter? Well, let's just compute. Remember, u plus v squared, we've done this a lot now, is u squared plus v squared plus uv plus vu. I hope you're okay with that. I skipped a little bit of a step right here, but then I need to add to it. Now what's this squared? It's going to be u squared plus v squared minus uv minus vu, the cross terms. And that will cancel that, and that will cancel that. And what do we have? The sum of the squares of the perimeter. U squared plus v squared plus u squared plus v squared. That's what we have. So we proved it. That's it. Okay, so I really did these last ones, number 8 through 12, differently than our book. I'm following a different book that I like better. So, I mean, I like how they do this better. Okay, I really like our linear algebra book too. Okay, see you next time.